This is FE Peer Review. The date is August the 22nd, 2021, in praise of more ignorance. This video is something of a follow-up to my previous video, which was a reprimanding of Kyle Adams for being overly willing to accept ignorance. It's in 3 parts. Part 1, no need to be fussy, but try not to be sloppy. Part 2, correcting some misconceptions regarding the globe model. This will give us a brief review of drop and Sagitta geometry. Part 3, the practical problems of carrying out the observation with value that math can bring towards making the observations a success. I came about the idea for this video from a video of Rachel's, and there were some comments that I'm responding to. I'm not really responding to Rachel's video here, but rather to some comments that were in the comment stream. We have a fellow named Just Barry, 1972. He says, I'll be doing, quote, remove the mystery tours later this year, where you will be able to physically see for yourself that water does not bend over 3 kilometers. Rachel responds, oh, what's that? Sounds interesting. Just Barry says, Stoke Bruern, 3 kilometer straight tunnel on the Grand Union Canal, fishing line pulled tight, close to the water surface, then a boat trip through the tunnel observing the line. On the subject of not being nitpicky but not being sloppy, the Blissworth Tunnel is not 3 kilometers long, it's 2.8 kilometers long. Here's a snippet from Wikipedia, and we can take a brief look at it on Google Earth. Here we've got Blissworth at the north, Stoke Bruern at the top. I've pinned the entrance and the exit of the tunnel. There you see the entrance of the canal into the tunnel at the south end. And at the north end, the exit of the tunnel at the north end. There's the continuation of the canal. And I made a path out of that. And if we look at the path, according to Google Earth, the path is 2.81 kilometers long. So I don't want to sound nitpicky, but let's try to get the details right if we're going to make a big deal over these numbers. Somebody named John Holland piped in. He seemed to know something about fishing lines. Over that distance, monofilament will give too many problems with stretch. Braid has very little stretch in comparison, but I'm sure you will see some sag. That's a key issue that we're going to explore. Your problem is if it touches the water in the middle, how do you tell if it's earth curve or line sag? And then John Holland went on to offer a very practical suggestion. Buy a 900 meter spool of 20-pound nylon and experiment with that distance first. Just Barry responded, I've already tested the line in the process of testing my knots, so he just kind of brushed away John Holland's very useful suggestion. Over 3 kilometers, one end of the tunnel would need to be about 80 centimeters lower or higher in space. It's visually straight, but over-indoctrinated think their line of sight follows Earth curve. Most ballers think their curve will be represented as a hump of water which would be about 40 centimeters deep in the middle. Laughing face. Well, Just Barry's got his numbers wrong. It's not 80 centimeters, it's more like 70. And it's not 40 centimeters, it's more like 18 or less than half. So he clearly doesn't understand the globe geometry. If Just Barry, who clearly is a flatty and wants to prove that the Earth is flat, intends to try to debunk the globe, he needs to know what the globe model is. And judging from the numbers he has used here, he doesn't. So my first advice to Just Barry, learn what the globe model is if you're going to try to disprove it. There are lots of resources out there for getting the math right. There's really no excuse not to get the math right. I will put links to some of these things in the description. Here's a video that shows all about how to calculate the Sagitta, which is what he was calling a bump or a hump or something. So there you go for the Sagitta. That's where I got the formula that determined the Sagitta was actually 0.18 meters or 18 centimeters. I Can Science That did a very nice video recently where he looks at various ways of deriving the drop measurement. I highly recommend that video, and there will be a link in the description. Just Barry, for your convenience, I'm providing this little cheat sheet here. It shows the numbers for the drop and the Sagitta and the calculations. The top diagram shows the drop calculation. We have somebody at one end on the left. We have a 3-kilometer line, and then we have the drop on the right. We have the equation here and the results. And the lower diagram shows the Sagitta. So we have a person at each end and a curve in between and a bulge. The bulge being a point connecting the base of one object to the base of the other, a straight line connecting those two bases. The Sagitta being the amount that the curve rises up above that straight line. And we again have the calculations here. And also look in the video description for some good videos on how to do this. So don't be sloppy. No need to be nitpicky, but don't be sloppy. It doesn't help. If you're going to be sloppy, then even if your results are correct, people are not going to be inclined to accept them. This is where I couldn't resist jumping in and joining the conversation, and it got, for me, quite a bit more interesting. I responded to Just Barry. If I understand you correctly, you're going to get a 3-kilometer length of fishing line and pull it tight. Have you calculated the force you will need to pull it into a straight line? If it turns out that for some reason you're not able to pull it into a straight line, have you got an idea what is an acceptable amount of sag and how to calculate and predict that sag so that it can be accounted for when measuring to the water's surface? I'd be interested to see your calculations for the previous 2 questions. I then touched on the issue of the Sagitta figures. Just Barry responded, you should come to Blissworth Tunnel and see for yourself. What do you think when sea fishing nets are pulled through the ocean? The largest is over 100 miles long and 18 miles wide. I responded about the nets. The nets are made of a material strong enough to resist the forces. Nonetheless, some do break. They also do not get pulled into straight lines. I found lots of pictures of fishing nets, which I thought of posting here, but I didn't want to dwell on this part of the subject. I want to get back now to what else he said. Barry said, I don't do calculations. I do real life and just observe. So calculations are not real life, and he does real life, which is obviously so much better than calculations. Calculations are just made up math stuff that's hard to get through. But real life is real life, and we really observe real life. That's all implied in that sentence there. It is, like Kyle Adams, a complete disrespect for knowledge. In fact, calculations are real life, and that's what I'm going to go on to discuss next. Before I get there, I'm going to just read one more comment I made in this comment stream. Well, that ticked me off, as you can probably guess, so I'll be very interested to see your results. Calculations are part of real life. Have you ever flown in an airplane? How are airplanes designed? Wing designs are tested in wind tunnels, real life. But a lot of calculations are done as well. This is why airplanes can fly, and you don't die when you get in one. I have an advanced degree in structural engineering. Among the things I designed were a few highway bridges. We didn't even have to bother with, quote, real-life testing, like for a wing design, because so much is known about the physical nature of the materials we use that we can design reliable highway bridges through calculation alone. It's a very efficient process. I would add here, because we don't have to do lots of physical testing, it costs us less money to design them, which means we can design more of them, which means that we are all as a society richer because we can have more roads and highways and bridges for less money because we're using math. Every time you get in a car, drive down the highway, and go over a bridge, that was made possible for you because of an engineer using calculations. Calculations are used to design the pumping system that gets water to your kitchen tap. Calculations were used to design the roof over your head so you would have a safe place to sleep at night. Calculations were even used to design the farming equipment that gets food from the field to the market and eventually to your table. So I encourage you to have a little more respect for the work of the people who made all this possible. You have roads to drive on, running water, food on your table, a roof over your head, because these people have the skill and intelligence to do the necessary calculations. If you can go back to the 17th century living if you want to, with its famines, epidemics, and without all the advancements such as automobiles, air travel, telecommunications, etc., and live your life as if calculations don't matter. Or you can acknowledge that you enjoy the 21st century lifestyle because of all the knowledge and skills of the engineers who made these systems possible. By the way, to pull that fishing line to a perfectly straight line, you will need an infinite amount of force. I could show you with calculations and save you a lot of trouble and expense. I could also show you how much force you will need to limit the sag to a specific amount, such as 2 inches, so that you can then obtain measurable results from your very interesting experiment. But I'm not going to do the calculation for you. If you want to have a successful experiment, you need to learn how to do it yourself. I can provide some suggestions for learning resources if you wish, just let me know. I'll give you a bit of advice. To pull that line to a 2-inch sag over 3 kilometers, you will need to apply so much force that the line will likely break. So again, failure. It could have been avoided if calculations had been done. If you want your experiment to be a success, you need hard numbers on the strength of the line, and then compare that to how much force you will need for a given amount of sag. If you don't or can't do those things, your efforts will be for naught. In the process of making this just now, I've decided to break this video into 2 parts. So I'm going to wrap up the first part here, and I'm going to make a second video, which I'll put up in the next couple of days, which gets into some more interesting issues about how to figure out what this rope fishing line needs to be, how strong it needs to be, how much force is going to be applied. And it's a kind of a fun first lesson in statics, which is the basis of structural engineering. I'm not going to do numbers. I'm going to focus on an intuitive conceptual approach to the issues so that at least folks like Just Barry can grasp the ideas, the concepts, even if they aren't comfortable with doing the math. I think Just Barry's experiment's a very fun idea. I'd love to see it happen. In fact, I'd love to be there if I possibly could when it actually does happen. But it would be really disappointing if the line broke and then they got a stronger line. They couldn't pull on it hard enough and it sagged so much it was dragging in the water. And then they got a stronger line and a better anchorage system, and they got it to the point where it wasn't dragging in the water, but they didn't know how much it was sagging, so the measurements that they got couldn't be used for anything because how much was sag and how much was earth curve. I mean, that would just be intensely frustrating, and it could all have been avoided by the use of math. So in the next video, we'll look at the structural engineering, the statics issues involved in this fun little experiment. That's enough for now. If you're enjoying these videos, please do like them, subscribe, leave comments. Thanks. Bye-bye.